Assalamu alaikum warahmatullahi wabarakatuhu. So today we will going to start our new chapter, which is induction motor. So far we have seen the basic principles of working principle of electric machines, in which we have seen how the transformer works and how the motor or generator works, and we have seen the transformer, their construction and their uses in daily life. Also, we have seen the synchronous generator and synchronous motor. Synchronous generators, as we know, they are widely used generators in the production of electricity, and while the synchronous motors have their wide use in power factor correction in the industrial loads. So today we will going to start the induction motor. So the basic working principle of induction motor is straightforward. Just like the synchronous motor generator, the stator of the induction motor is same and wounded as a three-phase winding, so that we can have the rotating magnetic field which is already produced, which is there because of the windings in the stator. The only difference is in the rotor and their working principle. So let's see how it works. As we have seen, the amortiguer windings on a synchronous motor could develop a starting torque without the necessity of supplying an external field current to them. So this was the method that we use to start the synchronous motor, as we learned that synchronous motors are not self-starting motors. So if we left the amortiguer windings in the winding without the DC main field at all, so a machine with only a continuous set of amortiguer windings is called an induction machine. So if we don't have any setup for the DC current, DC's field to apply to this rotor, and we just only have the amortiguer windings in the on the rotor, so that machine we call it as the simple induction machine. So such machines are called induction machines because the rotor voltage which produces the rotor current and the rotor magnetic field is induced in the rotor windings rather than being physically connected by wires. So the distinguishing feature of induction motor is that no DC field current is required to run the machine. So here we can understand one important tip about the induction motor is that they are self-starting machines. So we don't have to make any necessary arrangements to make the induction motor start. So induction motor has the same physical stator as the synchronous machine, and with the different rotor construction. So there are two different types of induction motor rotors which can be placed inside the stator. So one is called the cage rotor and other is known as the wound rotor. So the cage rotor consists of a series of conducting bars laid into slots carved in the face of the rotor and shorted either end by large shorting rings. So we have the bars and conducting bars, and they are actually shorted on each end. So the design is referred to as cage rotor because the conductors would look like one of the exercise wheels that squirrels or hamsters run. On the other hand, the wound rotor motor has a complete set of three-phase windings that are similar to the windings on the stator. So the three-phase of the rotor windings are usually Y-connected, and the ends of the three rotor wires are tied to slip rings on the rotor shaft. So the rotor windings are shorted through brushes riding on the slip rings, and the wound rotor induction motors therefore have their rotor currents accessible at the stator brushes. So where they can be examined and where extra resistance can be inserted into the rotor circuit. So these extra resistance is added to the wound rotor induction motor for different scenarios. Sometimes it is used to control the speed of the motor. So it is possible to take advantage of this feature to modify the torque speed characteristics of the motor, and the wound rotor inductions are more expensive than the cage induction motors, and they require much more maintenance because of the wear associated with their brushes and slip rings. So we, because just like we in the synchronous generator, we have seen that we have removed the slip rings to provide the DC to the rotor. So that was just because we actually don't want to make the machine in a wear and tear conditions, and we have to stop now and then to repair or to clean it and replace the brushes. So as a result, wound rotor induction motors are rarely used. So this is how this basic one stator of the induction motor looks like, and this is the rotor bars of the rotor, uh, conducting bars, and we have these shorting rings on both ends of this rotor. So this is a solid piece of actually solid piece of a rotor, and we can see that these bars are not straight; they are a little bit skewed. So this skewness is used so to avoid the interlocking of the poles, so that it may not lock, and we may lose the production of torque, as we will see in the next slides, that if they are straight and they can interlock with each other and can lose the capability of producing any torque. So these are few more pictures. Here we have this uh, solid cage rotor. This is how the cage looks like, and this is the uh, salient pole and wound rotors. There are some more pictures. Here's the wound rotor. We have these slip here. We will have the slip rings. The carbon brushes are used, which are used to short them, or we can add the resistance, or we can make the currents, whatever we want to do in the rotor. So this is how we can do it. So the development of induced torque in an induction motor. So induction motor operation is basically the same as that of the amortiguer windings on synchronous motors. So three set of voltages is applied to the stator, and a three-phase set of stator current is flowing. So these currents produce a magnetic field. We call it as the BS, which is rotating in a counterclockwise direction. The speed of the magnetic field's rotation is given by 120 F by P, where P is the number of poles of the machine and F is the supply frequency. So how this voltage is induced, this is we have seen previously, but let's look at it again. So there is a third major way in which a magnetic field interacts with its surroundings. So we have seen the different ways how this voltages, or how these magnetic fields and conductors interact with each other in different scenarios. So this is a scenario in which we have seen that how the voltage is induced. So if a wire with the proper orientation moves through a magnetic field, so these crosses shows that the magnetic field is uniform and moving into the page and going into the page, and this conductor is moving in this direction with the velocity v. So this will be the vector v cross b. So the voltage induced in the wire is given by V cross B and the dot product with the length of the wire. So where V is the velocity of the wire, B magnetic flux density vector, L is the length of conductor in the magnetic field. So where vector I points along the direction of the wire toward the end, making the smallest angle with respect to the V cross B. So this direction of L will be is such that the smallest angle, that V cross B angle, will be making with L. So the voltage in the wire will be built up so that the positive end is in the direction of V cross B. So if it is fundamental to the operation of all types of generators, for this reason it is called generator action. So this is how this voltage is induced, as we know that in the generator action. So the rotating magnetic field Bs passes over the rotor bars and induces a voltage in them. E induced is equal to V cross B dot I. It is relative motion of the rotor compared to the stator magnetic field that produces induced voltage in the rotor bar. Now here, what happens in this induction motor, that we have this Bs, which is the rotating magnetic field, and it is rotating in the counterclockwise direction. So it will induce this Bs will induce the voltage in the rotor, and rotor will try to rotate in the direction of Bs, because it will produce a unidirectional torque in the rotor. So it will start rotating slowly, and it will try to catch up this Bs. But this is not the synchronous motor, and we don't have any supply frequency. So what will happen? So that rotor will simply try to catch this Bs, but it will never catch up. So that it can never catch up this Bs is actually the relative motion, because there should be a Bs, and there should be a difference between Bs and the rotor magnetic field. So the velocity of the upper rotor bars relative to the magnetic field is to the right. So the induced voltage in the upper bar is out of the page, while the induced voltage in the lower bars is into the page. So here we can see now the result in the current flow out of the upper bars and into the lower bars. Since the rotor assembly is inductive, the peak rotor current lags behind the peak rotor voltage. So the rotor current flow produces a rotor magnetic field Br. So this is, here we have this Br. The induced torque is then Br cross product with Bs, where K is the constant, machine constant. So this will how this torque will be produced. So the resulting torque will be from Br to Bs, and that is in the counter clockwise direction. So the rotor accelerates in this direction, counterclockwise. I hope you have understood. So this is once again, see that this Bs is a rotating magnetic field, and because of this we have this Br induced in the rotor, and the cross product of Br cross Bs in the direction from Br to Bs, we can see that it is counterclockwise. So the rotor will rotate in the counterclockwise, and obviously it is producing a unidirectional torque. So that unidirectional torque will pull it in every rotation. So there is a finite upper limit of the motor's speed if the induction motor's rotor were turning at synchronous speed. So obviously we know that the rotor bars would be stationary relative to the magnetic field, and there would be no induced voltage. So if induced voltage is zero, obviously there will be no rotor current and no rotor magnetic field. So with no rotor magnetic field, the induced torque would be zero. So necessarily this never happens that the rotor reaches the synchronous speed, but we are assuming that if it by some means reaches the synchronous speed, then E induced will be zero. And when obviously induced voltage is zero, so there will be no current in the rotor, no magnetic field, and obviously if there is no magnetic field, we know that if Br is zero, then this whole term will be zero. So the induction motor can thus speed up to near synchronous speed, but it can never exactly reach synchronous speed. So note that in normal operation, both the rotor and stator magnetic fields Pr and Ps rotate together at synchronous speed, while the rotor itself turns at a slower speed. So this is very important thing to understand, that the relative motion is between the mechanical speed of the rotor and the synchronous speed of the rotating magnetic field. Although Br and Bs will rotate synchronously, but rotor itself will turn at the lower speed than the synchronous speed. So I hope you have understood so far. We will continue this induction motor in our next series of videos. So if you have any questions, please feel free to ask. Assalamu alaikum wa rahmatullahi wa barakatuh.